Hello everyone and welcome to another AP Computer Science video. We're trying to finish up our topic of recursion, and in today's video we're going to focus on one example of an implementation of something we've done before but through the iterative approach. Right, we've done searching, looking for values in lists or arrays or whatever they might be, and we have done this linearly, so with a linear search, meaning look at one spot at a time from beginning to end, and if we find a match, we return the index, otherwise we return -1. The order does not matter for our data. And then we saw a more efficient approach if we could assume that our data is sorted. So if we had sorted data, the binary search was a much more powerful tool and extremely efficient in finding values, no matter how large. And then we can have billions of values and it still would be extremely efficient in finding it, as opposed to linear search, where the more data you have, the harder it is to find something and the more time you might have to spend to find out that it's not even in a list. So what we're going to do is binary search is a situation where the recursive implementation actually is quite easy to understand, and it's the same premise, and it might even be more obvious to you than the iterative approach. And so we're going to try to implement that today. I'm going to make a new class, and if you don't remember, I'm going to quickly show you the iterative approach to binary search. We took in an array list of numbers and a value to search for. And we had a loop that would continue, and as long as the lower value and the upper value, those were the ranges of the list we were searching through, were in the correct order, so lower was smaller than upper, we would continue to search. We would split it in half, pick the middle. If that's the answer, then we are done. If it's not, then we decide, should we go to the lower half or the upper half? And then that was it. So now let's go ahead and see the same action, and if we somehow get out of this loop and manage to not find it, then we return -1. So let's do the same thing with recursion. So I want to make a new file in our recursion section, and we're going to call this binary search recursion. So we'll make a main, but we won't fill it in just yet. We will make our implementation and then try it out. I'm going to use an array of integers this time instead of an array list, just to try it a little bit differently, but the recursion is not tied to whether it's an array or an array list. So we'll say public static int, because remember we're returning an index. We'll call this binary search. There's no need to call it rec or anything like that, because there's no conflict with other binary search in a different class. Our input is going to be an array of integers, and then the value we are looking for. So again, the approach we take when it comes to recursion is a 3-step consideration. What is our base case? What is the situation where we know the answer immediately? What is the way we're going to shrink our problem? And then finally, when do we call the recursive method? When do we call binary search inside of itself? And is it going to be on a smaller problem? And that's the components we need to make sure we're aware of. And so let's think about that for a moment and say, well, what is the base case? What is the situation, given the array of values and the value, that we know the answer immediately? Right? We do actually have to maybe add some data, because we need to know where to start and where to begin. Unfortunately, because the recursion is going to be different, this one might not necessarily have enough information to make this happen. So we might have to take the approach of a helper method. If you look at the iterative approach, the reason we didn't need that is because we could make our variables in this method. There they are. These are basically the helper methods. But since there's no recursion going on, these variables kind of exist for the lifetime of this value, or for this loop, so this whole method. So they exist the whole time. In our recursion, remember, every time a method is called, it's kind of like a new version of the method is being run with different data points. And if we make the same start and end every time, same lower and upper every time, there will be no change to the problem. The goal here is to change the upper and lower. That's how we're going to shrink our problem. And so perhaps we should make an implementation that gives us that data so we can work with it. So let's go ahead and try that. We'll say, we'll do private static int, call it bin search, and this will be our recursive version. It has the same array of numbers, it has the same value we're looking for, but it also has where we start searching and where we end searching. This is what allows us to figure out where the middle happens to be. So we'll say lower and upper. So at the end of the day, the data is going to be very similar. What is the first thing we did in the iterative approach? Besides assuming lower and upper, in this case that was convenient, we won't do that here. We checked, are we still looking? So that's one base case we can handle. If this is not true, then we must be that there is no result, and therefore we return -1. So that could be our base case, the same question. If lower, well, so we're going to ask the opposite question, because this is a positive statement, so is this true, then keep looking. Otherwise, we're going to do the opposite. So we're going to say if lower is greater than upper, right? That's the exact opposite of less than or equal to upper. If lower is greater than upper, then it must mean that we have failed to find the answer. So let's return -1, right? So if we started looking at 0 and ending at length -1, and then somehow the lower becomes larger than length -1 or bigger than upper, then that means we didn't find a result. That's one base case. Another base case that we ended, so we can always match base cases if we're looking at return statements. So there's one, there's a second base case. In the situation that we found the middle, our middle was the lower plus the upper divided by 2. So let's take that line, we'll copy it, and we'll ask the same. We'll set up the same scenario. So there's our middle, and we'll ask the same question, right? If the value at the mid is what we're looking for, then we're done. So we're going to say if our array at mid is equal to the value, then we also have a base case, right? And the answer is it's not -1, and I didn't mean to put a space here. It's not -1, but it is whatever index we found it at, which is mid. So our answer is return mid, right? So far so good. And now the last step. Well, if we didn't fail to find it, and the middle's not the answer, then we need to search recursively through some section. But thankfully, the problem is going to get cut in half, just like it did in the original. And so our recursion will happen either on the left half, the smaller half, or the right half. And again, we're making the assumption, just like last time, that we're going from small to big. Our ordering is from small numbers to large numbers. So we can simply ask the same questions that we asked last time. Is that value less than the middle? So let's ask that. If the value is less than the array at mid, if that is the case, then we know we have to recursively search on the left side. So we'll return the recursive answer, bin search, and again, what is our input? Here's where we're going to shrink the problem and do the recursion at the same time. So we'll say the array is the same data. We're still looking for the same value. Since we're small in the middle, we're going to the left side. So what changes, the lower or the upper value? And if we look at our example last time, the upper changed to mid -1. So we will do the same thing. Our lower will be the same input, but our upper in this recursive call will be mid -1. And there it is. And then now the last possibility, I don't have to write an if statement because either it was equal, or it was less than, or it's greater than. So here I can simply do the recursion, and I can put a comment just so we know, val greater than array at mid. This is what's true here at this point, but we don't have to ask the question about it. We can simply return the same recursive search, but here our adjustment is of lower, and again, if you don't remember, we're saying the lower becomes mid +1. So we can say mid +1, and our upper remains the same, right? And so there's our result for the binary search, and this should work. Now, how do we call it in our public-facing version? Because they're not supposed to. The idea is that no one's supposed to use them except us, and so it's very simple. What we have to add is where do we start and where do we begin, and that matches the first part of our situation in the original, which is 0 and size -1 or length -1. So we can say the answer to this implementation is simply calling the recursive version bin search with the same array, the same value. Our initial lower is 0, and our initial upper is array.length -1, which is the last safe index. And there it is. Now to test this, we do need a sorted array of numbers. So let's go ahead and make an array of numbers. I'm going to maybe take some code from somewhere else to save ourselves some work. But let's go ahead and make an array of numbers. We'll say int array nums is equal to, and we'll just make a literal array with some random values. Actually, let's put them in order already so I don't have to sort them. I'm kind of be smart about this. 24, 35. Well, let's do 59, 107, 111, 150. And we'll do There it is. So it doesn't matter what the numbers are, but they are in sorted order. 7, 10, 13. Okay, there we go. So now let's search for them and let's see if we can find the values. So here we go. Let's just print out the result of the binary search on nums, and let's search for the number 35. We should get 0, 1, 2, 3, 4 as our answer. Let's see what happens. And there it is, the index 4. It looks good. Let's search for the number 7. We should get 0 as our answer because it is the first value. And there it is, 0. And now let's search for the number 10,500. Let's go ahead and run it. We should get the last index, which is 10, right? There are 11 items, and therefore it's 10. And let's do one last test. Let's look for the number 777, which is not in this array, and therefore we should get a -1. We've covered all scenarios, and there it is, right? And so this works nicely, and we could use negative numbers. The result is the same. The implementation is what's different. And in my opinion, this is a very simple implementation. There's no loops, there's no thing. It says, well, look, okay, if the lower is greater than the upper, then we failed to find it, we're done. If the middle happens to be what we're looking for, we're done. Otherwise, recursively search on the, if it's smaller, recursively search on the left side. Otherwise, recursively search on the right side. That's it. I mean, it is essentially the same implementation. We're still only going through half of the list every time. So in this case, every loop, we are going through half of the list. We're doing less and less work. In this situation, every recursion, we have less and less to look through. So it goes very, very, very quickly. Right? So we'll stop here. And in our last video on recursion, we're going to do one last thing. We're going to use a sort. So we've seen bubble sort, insertion sort, selection sort. We're going to do one sort, which is a recursive sort, called merge sort. And in fact, it's one of the most popular sorts for two main reasons. One, it is reasonably easy to implement if you understand the main parts of it. And it is pretty efficient in almost any scenario. We talked about the performance in terms of if we had to graph a representation of the overall performance or the number of comparisons a sort had, we said that bubble, insertion, and selection are considered n-squared algorithms because if there are n items, it takes n-squared comparisons. So it kind of decays in quality very quickly. Merge sort, as a recursive sort, because of the strategy it takes, is considered an n log n algorithm. This means almost linear. N is linear times the log of n, which is not a very big number. That's a pretty good approach. That means you don't have to do that much more work to sort it. And what makes it even more powerful, that merge sort, and we'll see this in the next video, is that if you give me a sorted list, it's still n log n, which is very good. If it's completely random, it's n log n. And if it's in reverse order, which is often a very ugly situation to be in, it's still n log n. Right? There are other sorts that exist that sometimes are really efficient and sometimes are not so great. So we'll see that recursion is really useful for implementing merge sort. Can merge sort be done iteratively? The answer is yes, but it is actually quite difficult to do, and so most people tend not to do it that way. So we'll do merge sort together in our last video, and that'll be the last discussion of recursion. And again, for the AP exam, you're not going to have to know all the technical details, but you should be able to read the code and understand it. If you can see this and understand what's happening, what's the base case, what's the recursion, what's the shrinking of the problem, then you're in good shape, I think, for the AP exam. So I'll see you all in the next video.